Today we're going to be talking about L'Hopital's rule. So L'Hopital's rule is a way to evaluate limits of indeterminate forms at 0 over 0 or infinity over infinity that we've run into a few times, but it uses derivatives to actually make it a little bit of a simpler derivative to find, or sorry, a simpler limit to find. So let's look at an example. Okay, the limit as x approaches 3 of x squared minus 9 over x minus 3. So if I wanted to evaluate this limit, those are really big. If I want to evaluate this limit, we would get 3 squared, which is 9 minus 9, over 3 minus 3, which would give us 0 over 0, which is that indeterminate form. Okay, so using the original method that we learned before, when we ran into this issue, we would look to factor or simplify, see if there's anything that we could cancel out. Okay, so using our original method, I could go to my function, x squared minus 9 factors into x plus 3 and x minus 3 over x minus 3. X minus 3 cancels out. So now I have the simplified limit of x plus 3 as x approaches 3. I would plug in 3 again. 3 plus 3, which would give us 6 for our final answer. Okay, not too terrible. Using L'Hopital's rule, we can actually get the exact same answer. And while for this simpler example, it's probably going to be the same amount of steps, in the future, it will actually save us a lot of time because not all functions are so easy to factor and cancel and simplify, but you can always use L'Hopital's if you get an indeterminate form. So L'Hopital's rule states that if I have the limit as x approaches a of fx over g of x and I get that 0 over 0 or infinity over infinity, then I can derive the top of the function and the bottom of the function separately. I'm not applying quotient rule. I'm deriving each part of the fraction separately and then evaluate the limit again. Okay, so let's actually see this in action. So if I wanted to evaluate this using L'Hopital's, I already got that 0 over 0, so I would derive the top, which would be equal to just 2x. We have 2x over the bottom. Derivative of x minus 3 would just be 1. So that's just 2x. Then I would evaluate it by plugging in 3, so 2 times 3, which would give us 6. So same answer. Slightly different function that we reduced down to get that same answer, but the exact same answer, which shows us that the original method and L'Hopital's that we're going to use today are both effective. Okay, so let's look at some more examples. Now up here, because it was just, our kind of starting one, I did not show the correct work that I want you to show when evaluating L'Hopital's. So one of the things that the College Board really frowns upon is writing that 0 over 0 because it is an indeterminate number. We have been told that you will be counted off for writing 0 over 0, so we're going to shy away from actually doing that. And what we're going to do is when we look at a limit and we think we're going to get that 0 over 0, or we think we're going to get that infinity over infinity or something like that, then we're just going to evaluate the top and the bottom separately. Okay, so let's look at number 2. So the limit as x approaches 2 of x cubed minus 8 over x minus 2. So just looking at this, it looks like I'm going to get that 0 over 0. So I'm going to say that the limit as x approaches 2 of 2 cubed minus 8, that would be equal to 0. And the limit as x approaches 2 of 2 minus 2 is equal to 0. Okay, so notice I'm not writing this as a fraction. I'm just evaluating the numerator and the denominator as if they're separate functions. Okay, so from here, I'm going to make this statement. So by L'Hopital's, okay, and now I'm going to apply my L'Hopital's rule. So 0 over 0 by L'Hopital's, the limit as x approaches 2 is equal to 3x squared over 1 in this case. Okay, and then I would evaluate it out. Okay, so 3x squared over 1, plug in 2, we would get 3 times 2 squared, which would be equal to 3 times 4, which is 12. Okay, so that is the full work that I want you to show every time. Evaluate the top, evaluate the bottom. If you get 0 and 0, or infinity and infinity, or negative infinity and negative infinity, those are your three indeterminate forms. Then you're going to write by L'Hopital's, and then take your derivatives and plug in. If by any chance you take your derivatives and you still get an indeterminate form, then you would just apply L'Hopital's again. You can actually apply L'Hopital's over and over and over until you get to a function you can evaluate. You can do it as many times as you need to. Fun little fact. Okay, let's do some more. Okay, the limit as x approaches infinity of the natural log of x over x. Okay, so the natural log of infinity, well, that would be equal to an infinitely big number because natural log just kind of goes out like that. Slowly increases as we go. It's going to increase slowly, but it does continue to increase forever. Okay, so we would say that's equal to infinity. Just infinity, well, that would be equal to infinity because x is just infinity, infinity on the bottom. So it's an infinitely bigger number on top being divided by an infinitely bigger number on the bottom. So it's infinity over infinity. So we write by L'Hopital's. And then we derive the top, which would be 1 over x, over derivative of the bottom, which is 1. So the limit as x approaches infinity of just 1 over x. Now we can plug in infinity, so we get 1 divided by infinity. And now, while that still is not a perfect number, if I have 1 being divided by an infinitely big number, what number is that basically going to be eventually? Well, it's going to be 0 because, I mean, if I'm divide 1 by a bazillion, it's going to be such a small number, I can say it's basically 0. So this would be 0. So unfortunately, if your indeterminate form is infinity or negative infinity, you're still going to have to do some guesswork more than likely at the end. Okay. Number 4, the limit as x approaches 0 of x over tan of x. So the limit as x approaches 0 of 0 would be equal to 0. The limit as x approaches 0 of tan of 0. Tan is sine over cosine, so 0 over 1, which would be 0. So we get 0 over 0. So by L'Hopital's, derivative of x would be 1. Derivative tangent is secant squared, so the limit as x approaches 0 of 1 over secant squared x. Then we would plug in 0, so that would give us 1 over secant squared of 0. Secant is the reciprocal of cosine. Cosine of 0 is 1. Reciprocal of 1 is 1, so 1 squared is 1. So we get 1 over 1, which is just equal to 1. All right. Now, last but not least, number 5. Now, number 5 looks a little tricky. Okay. The limit as x approaches 0 of 1 over x times the natural log of 2 plus x over 2. Because it doesn't quite look like a fraction. Like you're like, well, there's fractional things in there, but it's not written by a fraction. So just change it real quick. Okay. So this is the exact same thing as the natural log of 2 plus x over 2 all over x. So it's still a fraction. It's still that something over something, numerator or denominator. So now let's plug into both of them and see if we get 0 over 0. Okay. So the natural log of 2 plus 0 over 2 is equal to the natural log of 2, which is equal to, sorry, not natural log of 2, natural log of 2 over 2, which is equal to the natural log of 1, which is equal to 0. And then limit as x approaches 0. And I forgot to write on that one, so just add it up there. 0 is equal to 0. So we do still get that 0 over 0 for both of them. Okay. So for our final little piece, by L'Hopital's, this is probably a little bit more complicated derivative than the other ones, but not bad. So the derivative of natural log is u prime over u. So the derivative of u, so 2 plus x over 2, and that's going to be up here in the top of our fraction. The derivative of 2 plus x over 2, remember 2 plus x over 2 is just the same as 1 plus 1/2 x. So if I was to derive 1 over plus 1/2 x, that would just give me 1/2. Okay, so 1/2 over 2 plus x over 2, that's u prime over u, all over the derivative of just x, which would be just 1. Okay, so, and this is still the limit as x approaches 0. Okay, now I know it's a little bit of a mess, but we can evaluate from here. So plug in that 0, so we get 1/2 divided by 2 plus 0 over 2. Notice how I just dropped the 1 on the bottom, because if I'm dividing everything by 1, it's just itself. Okay, so this is equal to 1/2 over 2 over 2, which is just 1/2 over 1, which is just equal to 1/2. And there you have it. So the big thing with L'Hopital's, y'all, just make sure that you, when you are plugging in, that you plug them in separately. So limit of the top over limit of the bottom. Don't make it a fraction, okay, because we don't want to have that 0 over 0 result written anywhere on the page. Notice on all of my L'Hopital's answers, I never have 0 over 0 or infinity over infinity written, okay? And then once you get that result, derive the top, derive the bottom. Don't apply your quotient rule. You're just deriving each of them separately and then plug in again. If by any chance you derive, plug in, and you get an indeterminate result again, then you just repeat L'Hopital's. You can repeat L'Hopital's over and over and over until you can get a result.